Right now, there is a cup on a table somewhere. A ceramic cup, or a glass, or a metal travel mug. It does not matter. What matters is that it is there, sitting, occupying space, existing in the precise location it occupies, with the precise properties it has, whether or not anyone is looking at it, whether or not anyone has ever looked at it. The cup does not need a witness to be real. It simply is. Somewhere much further away, a star in the Virgo cluster is dying. It has been dying for millions of years, and it will continue dying long after every human being who has ever lived has been forgotten. It does not know we exist. We cannot see it clearly, but it is there, burning through its last reserves of fuel, collapsing under its own gravity, doing what stars do at the end of their lives in a specific location in space at this specific moment in time. And inside your hand, inside the atoms that make up the skin and bone and blood of the hand, holding whatever you are using to watch this video, there are particles spinning, electrons in their orbitals, protons and neutrons in nuclei, quarks inside those, each one existing, each one located somewhere, each one possessing properties, charge, spin, mass, that belong to it and to it alone, that it carries with it wherever it goes, that existed before you were born and will exist long after you are gone. These things exist, independently, separately, exactly where they are, with the properties they have, whether or not anyone observes them. That is not a scientific claim. It is older than science. It is the foundation of everything, of every bridge ever built, every crop ever planted, every journey ever taken, every prediction ever made. The cup is on the table when you are not looking at it. The star exists between the moments we observe it. The particle has a spin before we measure it. This is what philosophers call local realism. Locality. The idea that things are affected only by what is immediately around them, that a cause must travel to reach its effect, that nothing happening here can instantly affect something happening there. Realism. The idea that the universe has definite properties, whether or not anyone looks at it. You did not learn these things in school. You were born with them. They are older than language, older than civilization. They are so deeply embedded in the way the human mind models the world that questioning them does not feel like doing physics. It feels like going insane. Think about what local realism has allowed. Every prediction you have ever made about the physical world rests on it. You drop a cup and you know it will fall. Because you know gravity is local, it acts on the cup from below, not because something on the other side of the universe decided the cup should fall. You trust that the chair will hold your weight, because you trust that the atoms in the chair have definite structural properties that were there before you sat down. You plan your day around the assumption that the sun will rise, because the sun has been in roughly the same location in space for billions of years, and its location tomorrow will be predictably close to its location today. None of this works without local realism. The entire enterprise of science depends on it. The scientific method, observe, hypothesize, predict, test, only functions if the universe behaves consistently. If measurements reveal pre-existing facts, if what is true here is not simultaneously affected by something happening on the other side of the galaxy. Every laboratory experiment ever conducted assumed that the properties of the materials being tested belong to those materials and not to some non-local relationship between those materials and something very far away. We built civilization on this foundation, and we never questioned it because we never had to. It worked. It still works at every scale that human beings have ever inhabited. That is what makes what the Nobel Prize laureates proved so quietly devastating. Not that they discovered a flaw in a theory, they discovered a flaw in an assumption so fundamental that most physicists had never thought to write it down. You cannot overturn an assumption people did not know they were making. In 2022, 3 scientists were given the Nobel Prize in Physics, not for discovering something new, for proving something old was wrong. The story begins not with particles, but with a question about what science is allowed to ask. In the long history of science, there is a recurring pattern. A theory works, it predicts, it explains. Scientists use it to build things and navigate the world. And then, at some point, someone asks what the theory actually means, what it is saying about the underlying nature of reality, not just about the outcomes of measurements. And the answer to that question turns out to be much stranger than anyone expected. Newton's mechanics worked. It predicted planetary orbits, falling objects, the motion of pendulums. But Newton himself was deeply uncomfortable with the implications of gravity. Gravity, in his theory, acted instantaneously across empty space. The Earth pulls the Moon, the Sun pulls the Earth. The force reaches across millions of kilometers of nothing in no time at all. Newton found this strange. He wrote that the idea of one body acting on another at a distance, through a vacuum, without any intermediary, was so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He did not know what gravity was. He had described it mathematically with extraordinary precision, but he had no explanation for how it worked. It took Einstein and general relativity 200 years later to explain that gravity is not a force acting at a distance, but the curvature of space-time. The mystery Newton recognized was real, and it took 2 centuries to resolve. Quantum mechanics is in a similar position, except that the mystery is older and deeper and has resisted resolution for a full century. The theory works. It predicts. Its predictions have been confirmed to a precision that no other scientific theory in history has matched. And yet the question of what the theory is actually saying about reality, what it means for the universe to be quantum mechanical, remains genuinely, deeply, contentiously open. For most of human history, the question of whether the moon exists when no one is looking at it was not a scientific question. It was a philosophical one, interesting perhaps, but unanswerable by experiment, and therefore outside the domain of physics. Physics dealt with things you could measure. Whether unmeasured things had definite values was a question you could debate in lecture halls, but never settle in a laboratory. This changed. The way it changed is one of the most remarkable stories in the history of science. A story that spans 60 years, involves 2 of the most brilliant minds of the 20th century on opposite sides of a fundamental disagreement, and ends with an experiment that proved one of them definitively, irreversibly wrong. To understand what was proven, you need to understand what was at stake. And to understand that, you need to go back to the 1920s, when a group of physicists built a theory that worked perfectly and made no sense at all. The quantum revolution began with an embarrassment. In 1900, a German physicist named Max Planck was trying to explain a phenomenon called black body radiation, the way objects glow when heated, the specific colors they emit at specific temperatures. Classical physics, the physics of Newton and Maxwell, predicted a catastrophic result. An object should emit infinite energy at short wavelengths. This was called the ultraviolet catastrophe, and it obviously did not happen in reality. Heated objects glow in predictable, finite ways. But the equations said they should not. Planck found a mathematical fix. He assumed, as a temporary computational trick, that energy comes in discrete chunks, quanta, rather than a continuous flow. The math worked. The predictions matched experiment perfectly. The problem was, the trick was not a trick. It was describing something real. Energy really does come in discrete chunks. This was not a comfortable conclusion for anyone involved. What followed in the 1910s and 20s was a sustained collective confrontation with the strangeness of the very small. Niels Bohr proposed a model of the atom in which electrons occupy specific orbits and can jump between them by absorbing or emitting quanta of light. Werner Heisenberg developed matrix mechanics, a formulation of quantum physics so abstract that even its creator found it difficult to interpret physically. Erwin Schrödinger developed wave mechanics, a different mathematical formulation that turned out to be equivalent to Heisenberg's but easier to visualize, built around a wave function that described not the position of a particle, but the probability of finding it at any given location. The wave function was the most unsettling thing. A classical particle has a location. It is somewhere. The wave function of a quantum particle spreads out across space, assigning a probability to every possible location. When you measure the particle, you find it somewhere, and the wave function collapses to that location. But before measurement, the particle does not have a definite position. It has a range of possible positions, each with its own probability. This is not uncertainty in the ordinary sense, not the uncertainty of not knowing where your keys are when you could in principle find them if you looked. This is a deeper claim. The particle does not have a definite position. The question, where is this particle right now, does not have an answer. Not because the answer is hidden from us, because there is no answer. The position does not exist before measurement brings it into existence. If this sounds bizarre, that is because it is. There is no good analogy from everyday experience. The best that physicists have managed is to say that before measurement, the particle is in superposition, existing in multiple possible states simultaneously. This is not a metaphor. The mathematics describes it literally. The particle is here and there, and everywhere between, weighted by probability amplitudes, until an interaction with a measuring device forces it to be somewhere specific. The interference experiments that demonstrate superposition are not ambiguous. You can see the interference pattern with your own eyes. You can count the bright and dark fringes. You can track how the pattern changes when you add or remove the witch path detector. The data is not subtle. The quantum behavior of particles in superposition is as well established as any fact in physics. What is subtle is the interpretation. When we say the particle is in superposition, are we saying something about the particle or about our knowledge of the particle? Is the superposition an objective feature of the world or a description of our epistemic state? The Copenhagen interpretation, in its strictest form, refuses to answer. The wave function is a tool for predicting measurement outcomes. Whether it represents something real is a question that physics cannot answer. Bell's theorem and the experiments it generated have added a new dimension to this question. The non-locality that the experiments revealed is not just a feature of individual particles. It is a feature of quantum correlations. It tells us that the quantum description of entangled particles cannot be explained by attributing definite but unknown properties to each particle separately. Something about the joint description of both particles together, something that cannot be reduced to separate descriptions of each, is physically real and operationally significant. This makes the question of whether the wave function is real harder to dismiss. If the joint quantum state of entangled particles has real, measurable, non-local effects, it is difficult to maintain that the quantum state is merely a calculational tool with no reality of its own. And once it is somewhere specific, the wave function collapses. The spreading out probability distribution snaps into a point. The particle has a location. Until the next interaction, when the process begins again, the wave function collapse is one of the most discussed and least understood events in physics. Nobody agrees on what it means. Nobody agrees on what causes it. Nobody agrees on whether it is a physical process, a mathematical artifact, an update of our knowledge, or something else entirely. This disagreement is not peripheral to quantum mechanics. It is its central unresolved problem, and it has been unresolved since 1925. This raised an obvious and deeply uncomfortable question. If the particle does not have a definite position before measurement, where is it? The answer the mathematics seemed to give was, everywhere it might be, simultaneously. In what became known as superposition, a quantum particle exists in all its possible states at once until observation forces it into one. Erwin Schrödinger, trying to illustrate the absurdity of this idea when applied to macroscopic objects, proposed a thought experiment that has since become the most famous in physics. Imagine a cat in a sealed box, along with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers, the vial breaks, and the cat dies. If the atom does not decay, the cat lives. The atom, being a quantum object, is in superposition, simultaneously decayed and not decayed until observed. Therefore, by the logic of quantum mechanics, the cat is simultaneously dead and alive until someone opens the box. Schrödinger intended this as a reductio ad absurdum, a demonstration that something had gone wrong. You cannot have a cat that is simultaneously dead and alive. The superposition must end somewhere. There must be a boundary between the quantum world and the classical world. Where that boundary is, and what collapses the wave function, became the central interpretive problem of quantum mechanics. It remains unsolved today. The unsolved nature of this problem is itself remarkable. Quantum mechanics was formulated in the 1920s. A century of the most intense scientific activity in human history has passed. The theory has been tested to extraordinary precision. Its applications are everywhere. And the question of what happens when a quantum system is measured, what the wave function collapse actually is, has not been resolved. This is not for lack of trying. The interpretive problem is genuinely hard. Every proposed solution creates new difficulties. The Copenhagen interpretation dissolves the problem by refusing to engage with it, declaring measurement to be fundamental, and declining to ask what measurement is. This is pragmatically effective and philosophically unsatisfying. The many worlds interpretation solves the problem by saying nothing collapses but requires an infinity of parallel universes to do so. Objective collapse theories solve the problem by modifying the Schrödinger equation, but the modification has not been experimentally confirmed and introduces new parameters that the theory cannot explain. The measurement problem and the non-locality revealed by Bell's theorem are related. Both point to the same underlying strangeness in quantum mechanics. Both resist the same kind of classical intuition that assumes objects have definite properties at definite locations. The solution to one may require the solution to the other, or they may be two faces of a single deeper problem, a problem whose solution will require a revolution in our understanding of space, time, and measurement comparable to the revolution that produced quantum mechanics itself. Where that boundary is, and what collapses the wave function, became the central interpretive problem of quantum mechanics. It remains unsolved today. The double-slit experiment captures the strangeness most vividly. Fire a stream of particles, electrons, photons, even atoms at a barrier with two slits in it. And what you find on the detection screen behind is an interference pattern. Bright bands and dark bands, alternating. The signature of waves interfering with each other, constructively where the peaks align, and destructively where a peak meets a trough. This is not mysterious for water waves or light waves. But the particles are not waves. They are discrete objects. Each one should go through one slit or the other and land in a specific location on the screen. If you fire enough of them, you should get two bright patches behind the two slits, not an interference pattern, but you get the interference pattern. Each particle, individually, behaves as if it went through both slits simultaneously, as if it were a wave spread across the entire barrier, interfering with itself. If you add a detector to find out which slit the particle actually goes through, something remarkable happens. The interference pattern vanishes. Each particle now goes through one slit or the other, and two bright patches appear on the screen. The act of measurement, the act of finding out which path the particle took, changes which path the particle takes. This is not a result of disturbing the particle with the measurement. The effect occurs even when the measurement is designed to be as non-invasive as possible. It is not a technological limitation. It is a feature of how quantum mechanics works. The particle exists in superposition, going through both slits simultaneously until a measurement collapses the superposition and forces it through one. The measurement problem, why and how measurement collapses the wave function, is the central unsolved interpretive problem of quantum mechanics. It has been unsolved for 100 years. The various interpretations of quantum mechanics are, essentially, different answers to this question. And as we will see, the answer matters enormously for what quantum mechanics says about the nature of reality. Most working physicists in the 1920s and 30s adopted what became known as the Copenhagen interpretation, associated primarily with Niels Bohr. The Copenhagen interpretation is pragmatic to the point of being almost willfully incurious about reality. Its core instruction is, do not ask what is happening between measurements. The wave function gives you probabilities. Measurement gives you outcomes. The relationship between the two is governed by the Born rule. Use it. Calculate. Stop asking what is really going on. This pragmatism was enormously successful. Quantum mechanics, in its various formulations, made predictions of extraordinary precision. Its applications transformed the 20th century, transistors, lasers, MRI machines, the entire semiconductor industry. The theory worked. Most physicists decided that was enough. One physicist was not satisfied. Albert Einstein was 46 years old in 1925, when the modern formulation of quantum mechanics was being assembled around him. He was not a young revolutionary anymore, but it is worth taking a moment to understand who Einstein was in 1925, because it is easy, with the perspective of a century, to cast him as the stubborn conservative who refused to accept the new physics. That picture is almost entirely wrong. Einstein had been the most radical physicist of his generation. In the single year of 1905, working as a patent clerk in Bern, with no access to a university laboratory and minimal contact with the physics community, he had published 4 papers that each, individually, would have made his career. One explained the photoelectric effect using the quantum of light, a paper that would win him the Nobel Prize and that helped launch the quantum revolution. One explained Brownian motion and provided strong evidence for the existence of atoms, then still disputed. One introduced the special theory of relativity, overthrowing the Newtonian concepts of absolute space and time. and one derived the equivalence of mass and energy, E equals mc squared. In 1915, he published the general theory of relativity, replacing Newtonian gravity with the geometry of curved spacetime. This theory predicted that space itself could bend, that time ran at different rates in different gravitational fields, that massive objects would distort the fabric of the universe around them. It was verified experimentally in 1919 when the bending of starlight around the sun, predicted by general relativity, was measured during a solar eclipse. Einstein became, almost overnight, the most famous scientist in the world. This is the man who drew a line at quantum mechanics, not a conservative, not someone afraid of strange ideas, someone who had spent 20 years accepting stranger and stranger ideas about the universe and had found a place where the strangeness stopped making sense. His objection was not to quantum mechanics as a computational tool. He agreed it worked. His objection was to what it seemed to say about reality. And his objection was specific, principled, and, as it turned out, experimentally testable. He was not a young revolutionary anymore. He was the most famous scientist in the world, the author of 2 theories of relativity that had already rewritten the fundamental structure of space, time, and gravity. He had, in 1905, been among the first to propose that light comes in discrete quanta, an insight that would eventually win him the Nobel Prize, and that helped launch the quantum revolution he now found himself opposing. He was not opposing it from ignorance. He understood quantum mechanics as well as anyone. He had spent years probing it, testing it, looking for the crack that would reveal its incompleteness. His criticism was not the criticism of someone who had not done the work. It was the criticism of someone who had done the work carefully and found something that troubled him deeply. The historical caricature of Einstein as the stubborn conservative who refused to accept quantum mechanics is almost exactly wrong. Einstein's objection was not conservative. It was, in its own way, radical. He was arguing that quantum mechanics, for all its success, was describing only a shadow of reality, that the complete theory, when it arrived, would be stranger and richer than quantum mechanics, not simpler. Hidden variables were not a retreat to classical physics. They were a demand for a deeper physics, a physics that would explain the quantum probabilities rather than simply using them. He was wrong about hidden variables, as the Bell experiments eventually proved. But the underlying intuition that quantum mechanics is incomplete, that there is a deeper description of reality that we have not yet found, is still held by a significant minority of physicists. The search for quantum gravity, for a unified theory of the fundamental forces, for an explanation of why the constants of nature have the values they do, all of these are, in different ways, expressions of the conviction that quantum mechanics is not the final word. Einstein's ghost haunts modern physics, not because he was right about hidden variables, because he was right that the question of what quantum mechanics means about reality has not been satisfactorily answered. The nature of his trouble was specific and philosophical. Einstein believed in what the philosopher of science, Hans Reichenbach, had called the common cause principle. Whenever 2 events are correlated, either one causes the other, or they share a common cause. If measuring a particle in Paris instantly tells you the result of measuring a particle in Tokyo, there must be either a causal connection between the measurements or a common cause that predetermined both results. Quantum mechanics seemed to deny both options. It denied a direct causal connection. There was no signal traveling from Paris to Tokyo at any speed, and it denied a common cause. Bell would later prove that no hidden variables could explain the correlations. The correlations simply existed, without cause without explanation, without any mechanism that fit into the classical picture of reality. Einstein found this intolerable, not because he was conservative, but because he thought physics was supposed to explain things. A correlation without a cause was not an explanation. It was a mystery, dressed up in mathematics. A complete physical theory should tell you why the correlation existed, not merely that it did. Bohr's response, that the question of why was not a well-formed physical question, satisfied most of his contemporaries. It did not satisfy Einstein, and the fact that it did not satisfy him is part of why Bell's theorem exists. His objection was not to the mathematics, which he agreed worked. His objection was to what the mathematics seemed to imply about reality. Einstein believed in what he called local realism. He believed the universe was made of real things, with real properties, at real locations in space. He believed that nothing could influence anything else instantaneously across a distance, that causes had to travel to reach their effects, and that travel took time. He believed that God, as he put it, did not play dice, that if our description of the universe involved irreducible randomness, it was because our description was incomplete, not because the universe was fundamentally random. Quantum mechanics violated every one of these convictions. It described a universe of irreducible probability. It described particles without definite properties until measured. And it contained, Einstein eventually concluded, something even worse. Before the EPR paper, the debate between Einstein and Bohr had been largely a debate about the right way to think about quantum mechanics, about the right way to interpret a theory that both agreed worked. The EPR paper changed the terms of the debate. It made a specific, testable claim. If quantum mechanics was complete, if there were no hidden variables, then measuring one particle of an entangled pair must somehow instantly affect the other, regardless of distance. This, Einstein argued, was impossible. Therefore, quantum mechanics must be incomplete. The structure of the argument is important. Einstein was not saying quantum mechanics was wrong. He was saying it was incomplete, that it was describing only part of the story, and that the complete story would restore local realism. Hidden variables existed, we just had not found them yet. In 1935, Einstein published a paper with two colleagues, Boris Podolsky and Nathan Rosen. In 1935, Einstein published a paper with two colleagues, Boris Podolsky and Nathan Rosen. The paper is known by their initials, the EPR paper. Its full title is a question: can quantum mechanical description of physical reality be considered complete? Einstein's answer was no, and his argument was built around a phenomenon that would eventually become the most important concept in modern quantum physics: entanglement. Before we get to the argument, it is worth understanding what entanglement is at the level of the mathematics. When two quantum particles interact, their wave functions can become linked. The technical term is that they can no longer be described by independent wave functions. There is only one wave function for the pair, a single mathematical object that describes the combined state of both particles simultaneously. This combined state cannot be factored into two separate states, one for each particle. The particles are, in the mathematical sense, one system. This remains true regardless of how far apart the particles travel after the interaction. The wave function linking them does not diminish with distance. It does not weaken or degrade. It persists. The two particles remain mathematically one system, even if one is on Earth and the other is on the other side of the galaxy. When you measure one particle of an entangled pair, the combined wave function collapses. Both particles simultaneously acquire definite states, states that are correlated in a specific way determined by the original entangled state. The correlation is instant, regardless of the distance between the particles. This is the phenomenon Einstein could not accept. The EPR argument works like this. Imagine two particles that interact and become entangled. Their quantum states linked by the interaction. They separate. One travels to the left, one to the right. They move apart. Eventually, they are separated by a large distance, across a room, across a city, across the galaxy. It does not matter how far. Quantum mechanics describes these two particles with a single wave function, a single mathematical object that encompasses both of them, regardless of the distance between them. When you measure one particle, the wave function collapses, and you instantly know the state of the other, not because you measured the other, because they are entangled. If you measure the spin of the left particle and find it pointing up, you instantly know the right particle's spin is pointing down. The correlation is perfect. The knowledge is instant. Einstein saw two possible explanations for this. Either the particles were correlated before they separated, they always had definite opposite spins. You just did not know which was which until you measured one, or measuring one particle somehow instantly determined the state of the other, regardless of the distance between them. The first option meant quantum mechanics was incomplete. It described probabilities rather than certainties, not because the universe was fundamentally probabilistic, but because there were hidden variables, information the theory did not capture, that determined the outcomes in advance. The second option meant that measuring a particle in one location could instantly affect a particle in another location, no matter how distant. Einstein called this spooky action at a distance. He found it abhorrent. Nothing travels faster than light. If measuring one particle instantly determines another, something is traveling between them instantaneously, but nothing can travel instantaneously. Therefore, the second option is impossible. Therefore, the first option must be correct. Quantum mechanics is incomplete. The particles had definite states all along. We just did not know them. There must be hidden variables. Niels Bohr responded. His response is, famously, difficult to pass. He argued that Einstein's analysis assumed a classical picture of physical reality that quantum mechanics had already shown to be wrong. The particles do not have definite states before measurement. Measurement does not reveal a pre-existing state. It creates a state. Before measurement, the question, what spin does this particle have, does not have an answer. Not because we do not know, because there is nothing to know. Einstein found this response unsatisfying. They argued. They debated in letters and in person and in papers. They were friends who disagreed profoundly about what the universe was made of. Einstein died in April of 1955 in Princeton, New Jersey. He still believed quantum mechanics was incomplete. He still believed hidden variables existed. He never found them. And for a decade after his death, the debate seemed like it would simply remain unresolved, a philosophical dispute that experiments could never settle, that would persist as long as physicists disagreed about what physics was allowed to ask. Then, in 1964, a man named John Stuart Bell sat down in his spare time and changed everything. John Stuart Bell was born in Belfast in 1928, the son of a horse dealer. He grew up in a working-class family with no particular tradition of academic achievement. He was the first member of his family to attend university. He was, by accounts of those who knew him, a modest and unpretentious man who happened to have one of the sharpest minds in 20th century physics. He came to quantum foundations the same way many physicists of his generation did, through dissatisfaction. He learned quantum mechanics from textbooks that presented the Copenhagen interpretation as settled fact, and he found the presentation unsatisfying. Not the mathematics. The mathematics was clearly correct. The physical interpretation, the insistence that you could not ask what the wave function represented, that measurement was fundamental, that the act of observation played a role in physics, struck him as incomplete. He wanted to know what was really going on. He was aware of the EPR paper, he was aware of the debate between Einstein and Bohr, and he read at some point in the 1950s a paper by David Bohm. David Bohm was an American physicist who had, in 1952, done what Einstein had always claimed was possible. He had constructed a version of quantum mechanics with hidden variables. Bohm's theory, now called pilot wave theory or Bohmian mechanics, described particles with definite positions guided by a wave function. The particles were real, definite, local. The wave function guided them non-locally. Changes in the wave function propagated instantaneously. But the particles themselves were definite. Bell read Bohm's paper and was struck by two things. First, that it was possible to construct a consistent hidden variable theory that reproduced all of quantum mechanics' predictions. Einstein had been right that hidden variables were possible. Second, that Bohm's theory was explicitly non-local. The wave function's influence propagated instantaneously. You could have hidden variables, but only at the cost of non-locality. Bell began to wonder if this was a coincidence or a necessity. Could you have local hidden variables? Could you restore both realism and locality simultaneously? Or was non-locality the unavoidable price of any deterministic theory that reproduced quantum mechanics? Bell was an Irish physicist working at CERN, the particle physics laboratory in Geneva. His primary work was accelerator physics. Quantum foundations, the question of what quantum mechanics actually meant about reality, was a side interest, pursued in the margins of his regular work. In the culture of physics at the time, it was not a respectable interest. The working physicist's motto was shut up and calculate. The question of whether the moon exists when no one is looking was not the kind of thing serious people devoted their careers to. Bell was serious enough about it to work on it anyway. His insight was this: the two sides of the debate, Einstein's hidden variables versus Bohr's quantum non-locality, did not just make different philosophical claims about the nature of reality. They made different mathematical predictions about the outcomes of actual experiments. Measurably, experimentally different predictions. If you take two entangled particles and measure them repeatedly, at different angles, the correlations between their results have a specific statistical structure. If hidden variables exist, if the particles were carrying predetermined information from the moment of their entanglement, those correlations are bounded. They cannot exceed a certain mathematical limit. Bell worked out what that limit was. If hidden variables do not exist, if quantum mechanics is correct and the particles are genuinely in superposition until measured, genuinely entangled in the way quantum mechanics describes, then the correlations will exceed that limit. They will violate what Bell called his inequality. This was a profound intellectual achievement. Bell had transformed a philosophical question about the nature of reality into a testable prediction. He had given physics a way to ask the universe directly whether Einstein or Bohr was right. He had made the unanswerable answerable. It is worth pausing here to appreciate the human scale of what Bell did. He was not the most famous physicist of his generation. He was not working at the most prestigious institution. He was not pursuing this work as his primary career. It was a spare time interest. He published his paper in a small journal that few physicists read, and yet the paper changed the direction of physics. It opened a line of experimental work that has produced one of the most important results in the history of science. It inspired a generation of physicists to devote careers to experiments that most of their colleagues considered unnecessary. Clauser was warned off. Aspect was told it would ruin his career. Each of them proceeded anyway. The history of science is full of moments like this. A marginal figure asks a question that the mainstream considers unimportant or already answered. The question turns out to be the right question. The answer turns out to be revolutionary. What distinguishes the people who ask the right questions is often not genius in the conventional sense. It is stubbornness, the refusal to accept a non-answer as an answer. Bell refused to accept "shut up and calculate" as sufficient. He believed the question of what the equations meant about reality was a real question, and that finding the answer was worth the career risk. He was right. The questions mattered more than anyone knew. The CHSH version of Bell's inequality, named for Clauser, Horn, Shimony, and Holt, who refined Bell's work in 1969, sets the limit precisely. If particles behave like classical objects carrying hidden information, measurements at different angle combinations must produce correlations that sum to no more than 2. Quantum mechanics predicts a maximum violation reaching 2 times the square root of 2, approximately 2.83. The gap is small, but it is measurable. Before the analogy, it is worth dwelling on what Bell actually did. He found a way to distinguish between two theories that made exactly the same predictions for every individual measurement. Hidden variables and quantum non-locality both predict the same outcome when you measure one entangled particle. They both predict the same outcome when you measure the other. The difference only appears when you look at the correlations between many pairs of measurements at many different angles. And the difference, as Bell showed, is mathematically precise. This is a deep insight about the structure of physical theories. Two theories can agree on every individual event and disagree on the statistical relationships between events. The statistical relationships, the correlations, contain information that the individual events do not. Bell found the specific correlation pattern that distinguishes a local universe from a non-local one. He found the fingerprint of non-locality in the statistics. To make the idea concrete, imagine two gloves from the same pair placed in sealed boxes and shipped to opposite sides of the world. When you open your box and find a left glove, you instantly know the other box contains a right glove. There is nothing mysterious here. The information was carried in the gloves from the moment they were packed. This is the hidden variable picture. The particles, like the gloves, always had their properties. We just did not know them. Bell's inequality tests whether particles behave like gloves. If the experimental results stay within the classical limit of 2, they do. If the results violate that limit, if they reach the quantum prediction of 2.83, they do not. The particles were not carrying predetermined information. There was no pre-existing left glove and right glove. Something else was happening. In 1964, no laboratory in the world had the technology to run this test. Bell published his paper. Almost no one read it. The experiment he had made possible would have to wait for the tools to catch up with the theory. They did not wait long. John Clauser encountered Bell's paper as a graduate student at Columbia University in the late 1960s. He read it carefully. He understood what it meant. He decided he wanted to run the experiment. His advisors were not enthusiastic. The conventional wisdom among physicists was that hidden variables were obviously wrong and quantum mechanics was obviously right, and the whole question was a waste of time. Running an experiment to settle a debate that was already settled, just not experimentally, was not the kind of thing that built careers. Clauser was warned off. He ignored the warnings. After completing his PhD, he moved to the University of California, Berkeley as a postdoctoral researcher. By 1972, working with Stuart Friedman, he had built an apparatus capable of producing pairs of entangled photons and measuring their polarizations at different angles. The photons came from calcium atoms excited by a laser. The atom emitted two photons in rapid succession, their polarizations entangled with each other. Polarizers and detectors measured the photons as they traveled in opposite directions. The equipment was improvised and crude by later standards. The detectors missed most photons. The data collection was slow. The statistical analysis required months. This was frontier experimental physics, not the elegant, purpose-built apparatus of a well-funded laboratory, but the kind of science that gets done when a single determined researcher decides that a question matters enough to pursue it against institutional indifference. Clauser and Friedman measured the correlations between their entangled photons at 4 different angle combinations. For each combination, they counted the coincidences, the events where both detectors registered a photon at the same time, and calculated the correlation coefficient. They then combined these coefficients in the way Bell's inequality specified. If hidden variables existed, the result would be at most 2. If quantum mechanics was right and hidden variables did not exist, the result would be closer to 2.83. The experiment ran. The results came in. Bell's inequality was violated. The correlations between the entangled photons exceeded the classical limit. Not by a small margin, significantly. The data was consistent with quantum mechanics and inconsistent with any theory of local hidden variables. The particles had not been carrying predetermined information. There was no pre-existing glove in each box, but there were loopholes. The detectors Clauser used were not efficient enough to detect every photon. Most photons were missed. The statistical analysis assumed that the detected photons were representative of all photons. A reasonable assumption, but an assumption. If this assumption was wrong in a specific way, the results could be misleading. This was called the detection loophole, or the fair sampling loophole. There was also the locality loophole. The detectors in Clauser's experiment were close together. It was possible, in principle, that information about the setting of one detector was influencing the result at the other, not through any mysterious quantum mechanism, but simply by traveling from one to the other at the speed of light before the measurement was complete. If the measurement settings were chosen and the measurements completed before a light speed signal could travel between the detectors, this loophole would be closed. Clauser's setup did not do this. The universe had spoken. But it had left enough escape routes that determined skeptics could still doubt. Clauser himself, as noted, was among those who doubted. He spent years after the experiment looking for explanations other than genuine quantum non-locality. He explored the possibility that the detection efficiency loophole was masking a hidden variable result. He considered modifications to quantum mechanics that might restore local realism. He did not find any that worked. This is worth emphasizing. The man who first experimentally demonstrated the violation of Bell's inequality spent years afterward trying to prove his own result wrong. He was not satisfied by the data. He wanted a different answer, and he looked hard for it. He did not find it. The scientific community's response to Clauser's experiment was mixed. Some physicists were excited. Others were indifferent. The Copenhagen interpretation had always told them that questions about hidden variables were meaningless, so proving hidden variables didn't exist felt like proving that a question that couldn't be asked had no answer. The result was important, but it was hard to agree on exactly why. Bell himself was cautious. He recognized the significance of Clause's result, but also recognized the loopholes. He wrote and spoke about the need for better experiments that would close the loopholes and provide a definitive answer. He did not live to see the definitive answer, but he set the agenda that would eventually produce it. The escape routes would be closed, one by one, over the following decades. Alain Aspect was a French physicist working at the Institut d'Optique in Orsay, near Paris, in the early 1980s. He had been thinking about Bell's theorem since reading Bell's paper as a graduate student, and he decided he wanted to run a version of the experiment that would address the most important remaining loophole, the locality loophole. Before he began, he visited John Bell in Geneva to discuss the experiment. Bell, according to accounts of the meeting, asked him how long he had until his PhD defense. When Aspect said a few years, Bell suggested that was brave. The implication was clear. This was not a project that would make a career. It was a project that might end one. Aspect proceeded. He spent years building his apparatus. He designed a new kind of entangled photon source, calcium atoms excited by two lasers simultaneously, producing pairs of photons with entangled polarizations at a much higher rate than Clause's setup had managed. He built more efficient detectors, and he developed the switching mechanism that would be the key innovation of his experiment. The switching mechanism worked by rapidly changing the orientation of the polarizers while the photons were in flight. A photon takes a specific amount of time to travel from the source to the detector. If the polarizer setting could be changed in less time than it took a light-speed signal to travel from one detector to the other, the two measurements would be truly independent. No information from the setting of one polarizer could reach the other before the measurement was complete. Aspect's first experiments used a periodic switching mechanism. The polarizers alternated between two settings at a fixed frequency. This was fast enough to close the locality loophole in principle. But periodic was a problem. A sophisticated hidden variable theory could, in principle, exploit the regularity of the switching to coordinate the results. The switching needed to be random, not periodic. Later versions of the experiment used a more sophisticated random switching mechanism. The results in all cases were the same. The key innovation in Aspect's design was timing. His detectors were far enough apart that a light-speed signal could not travel from one to the other during the measurement. But more importantly, the measurement settings, the angles at which the polarizers were oriented, were switched randomly after the photons had already been emitted and were in flight. This was crucial. If the photons somehow carried information about the experimental setup, they could only carry information about the setup at the moment of emission. By switching the settings after emission, Aspect ensured that no physical signal from either detector could reach the other in time to influence the result. The two measurements were, in the technical sense, space-like separated, outside each other's light cones. No signal could connect them. He also improved the photon source and the detectors. The violations of Bell's inequality in his experiments were enormous. Many standard deviations above the classical limit, far beyond anything that could be attributed to chance or experimental error. In statistics, 5 standard deviations is considered sufficient to claim a discovery. 50 is not a borderline result, it is a verdict. The data was unambiguous, but a careful physicist could still point to remaining loopholes. The detectors were still not perfectly efficient. The switching mechanism was fast but periodic. A sophisticated hidden variable theory might, in principle, exploit the periodicity. The scientific community recognized Aspect's experiments as strong and convincing, but not definitive. What was needed was an experiment that closed all major loopholes simultaneously. That experiment was still 30 years away. While the experimental work was progressing, Anton Zeilinger was doing something different. He was not just testing whether entanglement violated Bell's inequality. He was exploring what entanglement could do. Zeilinger, an Austrian physicist working first in Vienna and later at the University of Vienna, became interested in the operational possibilities of entanglement, not just as a test of quantum mechanics, but as a resource. If two particles were genuinely entangled in the way quantum mechanics described, what could you do with that entanglement? In 1997, his team in Innsbruck achieved quantum teleportation for the first time. Not the teleportation of matter, not the Star Trek version, the teleportation of a quantum state. The complete quantum information describing the state of a photon was destroyed in one location and recreated in another, using an entangled pair as the channel. This is not science fiction, but it is genuinely strange. The quantum state of the original photon, every piece of information needed to completely describe it, was transferred to a different photon in a different location. The original photon was changed beyond recovery in the process. The receiving photon, which had never interacted with the original, became an exact quantum replica, and it was instantaneous. The state transfer did not travel at the speed of light. It did not travel at any speed. It was a correlation established across a distance that, at the quantum level, was not a meaningful separation. It is worth dwelling on what quantum teleportation actually demonstrates, because it is frequently misunderstood. What Zeilinger's team teleported in 1997 was not a particle. They did not disassemble a photon in Innsbruck and reassemble it somewhere else. What they transferred was the quantum state of a photon, the complete description of all its quantum properties, from one photon to another. The original photon, in the process of having its state measured as part of the teleportation protocol, had its quantum state destroyed. The receiving photon, which had never interacted with the original, became an exact quantum replica. The process uses an entangled pair as a resource. The particle whose state you want to teleport is brought into contact with one half of an entangled pair. A specific measurement is made, a so-called Bell state measurement that entangles the state of the original particle with the half pair it touched. The result of this measurement, just two classical bits of information, is sent by ordinary means to the location of the other half of the entangled pair. When the receiver applies the appropriate operation based on those two bits, they produce a particle in exactly the quantum state of the original. The quantum state was transported, not through space in any ordinary sense, through the entanglement that pre-existed between the two locations. Two classical bits of information had to travel the ordinary way. The quantum teleportation itself was instantaneous, but without those two classical bits, limited by the speed of light, the receiver cannot complete the reconstruction. This is why quantum teleportation does not allow faster-than-light communication. The classical channel is the bottleneck, but the quantum state transfer was real, instantaneous, and performed across an entangled channel that connected two particles which had never directly interacted. The entanglement did the work. The entanglement was the resource. This is not a curiosity. Quantum teleportation is one of the fundamental protocols of quantum communication. It is used in quantum cryptography, in distributed quantum computing, in quantum networks. The quantum internet, the network that will allow quantum processors to communicate and collaborate across arbitrary distances, will be built on protocols that Zeilinger's group demonstrated in that Innsbruck laboratory. Zeilinger extended the distances. Working with colleagues, he demonstrated entanglement over increasingly long baselines, first across a laboratory, then across Vienna, then between the Canary Islands. In an experiment conducted between the islands of La Palma and Tenerife, entangled photons were transmitted and detected across 143 kilometers of open air. The correlations held perfectly. And then came the satellite. In 2016, China launched a satellite called Misius, named after an ancient Chinese philosopher. It was the world's first quantum communications satellite, designed to distribute entangled photons between ground stations far below. In 2017, the Chinese team, led by Jianwei Pan, working with Zeilinger and international collaborators, published results demonstrating entanglement between two ground stations separated by over 1,200 kilometers on opposite sides of a mountain range, with a satellite in orbit above them mediating the entangled photon pairs. The technical challenge of this experiment is difficult to appreciate without context. Sending individual photons through the atmosphere is notoriously difficult. The atmosphere scatters and absorbs light. A single photon is extraordinarily fragile. A random interaction with an air molecule can destroy it entirely. Sending individual photons from space to the ground through the entire thickness of the atmosphere, maintaining the quantum entanglement of those photons over the journey, and detecting them reliably at ground stations separated by over 1,000 kilometers, required years of engineering and multiple technical breakthroughs. The experiment worked. The entangled photon pairs arrived at the ground stations. The Bell inequality was violated. The correlations between particles separated by over 1,000 kilometers matched the quantum mechanical predictions with high precision. And this was just the beginning. The Misius satellite went on to demonstrate quantum key distribution, using entanglement to distribute cryptographic keys that are, in principle, impossible to intercept without detection. Between ground stations in China and Austria, a distance of over 7,000 kilometers. The quantum internet, which would use entanglement to enable communication that is fundamentally secure against eavesdropping, is being built. Its foundations were laid by the experiments that began in Clause's improvised Berkeley laboratory and extended to a satellite named after an ancient philosopher circling the Earth. Entanglement is not just a philosophical curiosity about the nature of reality. It is a physical resource, a technology, something that can be generated, manipulated, distributed, and exploited for practical purposes. The quantum computers, now being developed by Google, IBM, and others, use entanglement as a computational resource. The ability of qubits to be entangled with each other gives quantum computers capabilities that classical computers cannot replicate. The Nobel Prize recognized both aspects of what Clause, Aspect, and Zeilinger achieved. The philosophical proof that local realism is false, and the technological foundation that entanglement is real and usable. The two aspects are inseparable. You cannot build a quantum computer without understanding what entanglement is. And understanding what entanglement is requires accepting what the Bell experiments proved. Before the quantum computer, there is quantum cryptography. And quantum cryptography is perhaps the most immediately practical consequence of entanglement, and the most immediate demonstration that non-locality is not just a philosophical curiosity. In ordinary cryptography, security depends on computational difficulty. You encrypt a message with a key. The security of the encryption rests on the assumption that the key cannot be calculated by an attacker, that the mathematical problem of finding the key from the encrypted message is computationally intractable. This assumption has held for decades, but it is always a contingent security, dependent on what computing power is available, and vulnerable to new mathematical discoveries or new computational hardware. Quantum key distribution is different. Using entangled photon pairs, two parties can establish a shared cryptographic key with a security guarantee that is not computational but physical. Any attempt to intercept the key, to measure the photons in transit, will disturb the quantum states of the photons, because measurement disturbs quantum systems. The disturbance is detectable. If an eavesdropper has intercepted the key, the recipients will know, because the correlations between their photons will be different from what quantum mechanics predicts for undisturbed entangled pairs. The security guarantee is not, "This is hard to break." It is, "Any breaking leaves evidence, and the evidence is detectable." This is a fundamentally different kind of security guarantee, and it follows directly from the quantum mechanical properties that Bell's experiments confirmed. Quantum key distribution systems are already commercially available and already in use in high-security applications. Banks, governments, and telecommunications companies are deploying quantum cryptographic networks. The first quantum communication satellite, China's Mycius, demonstrated quantum key distribution from space to the ground over thousands of kilometers. The quantum internet, connecting quantum processors and enabling provably secure communication worldwide, is under active development. All of this rests on the foundation that Clauser, Aspect, and Zeilinger built. The entanglement is real. The non-locality is real. The correlations that Bell's theorem identified and the experiments confirmed are not philosophical abstractions. They are engineering specifications. The quantum computer is worth dwelling on because it illustrates the practical weight of what the Bell experiments demonstrated. A classical computer processes information in bits. Each bit is either 0 or 1. A classical computer with 1,000 bits has a specific state at any given moment, a specific string of zeros and ones. When it computes, it processes one state at a time, following a sequence of logical operations from input to output. A quantum computer processes information in qubits. Each qubit, like any quantum system, can be in superposition simultaneously 0 and 1, with specific probability amplitudes for each. And qubits can be entangled with each other. A quantum computer with 1,000 qubits does not have a single state. It exists in superposition across 2 to the power of 1,000 states simultaneously, a number so large it is effectively incomprehensible. Every computation it performs operates on all those states at once. This is not faster classical computation. It is a qualitatively different kind of computation. Certain problems that would take a classical computer longer than the age of the universe to solve can in principle be solved by a sufficiently large quantum computer in seconds. Cryptography, drug discovery, materials science, optimization problems of enormous complexity. These are the domains where quantum computers promise to transform what is computationally possible. The quantum computer works because entanglement is real. Because the correlations between qubits are not the correlations of classical systems carrying hidden information, they are the deeper, non-local correlations that Bell's inequality tests for. The computational power comes precisely from the quantum nature of the correlations. If local hidden variables were real, if the qubits were actually in definite states all along, and quantum mechanics was just hiding that from us, quantum computers would not work the way they do. The computational advantage would vanish. Every successful quantum computation is, in a small way, a confirmation of Bell's theorem. Every qubit entangled with another qubit is a practical demonstration of non-locality. The foundations are not separate from the applications. The philosophy is not separate from the engineering. The question of whether reality is locally real turns out to have direct consequences for the most powerful computers humanity is currently building. Over 1,200 kilometers. The Bell inequality violated. The correlations between the entangled photons measured on opposite sides of a mountain range, mediated by a satellite in space, matched the quantum mechanical prediction with high precision. The distance between the particles was irrelevant. It had always been irrelevant. The experiments were simply making the irrelevance undeniable at scales that human beings could feel. In 2015, a team led by Ronald Hansen at Delft University in the Netherlands did something the field had been working toward for 50 years. The experiment took more than 2 years to design, build, and run. The challenge was not any single technical problem, but the requirement to solve multiple difficult problems simultaneously. Closing the detection loophole required detectors of near-perfect efficiency. Closing the locality loophole required large physical separation and fast random switching. Closing the freedom of choice loophole required measurement settings chosen by a process that could not have been influenced by the particle source. The team chose to use electrons rather than photons. Specifically, electrons trapped in nitrogen vacancy centers in diamonds. These are natural defects in diamond crystals, where a nitrogen atom sits next to an empty lattice site, creating a system that can trap a single electron and manipulate its quantum spin. The spin of the electron could serve as the qubit whose properties were measured. The two diamonds were placed in laboratories 1.3 kilometers apart at opposite ends of the Delft University campus. The electron spins in each diamond were entangled not directly across 1.3 kilometers. The direct entanglement would be technically impossible, but through an intermediary process. Each electron was first entangled with a photon. The photons from both labs were sent through optical fibers to a central station halfway between them, where a measurement was made that entangled the two photons with each other. Because each electron was entangled with a photon, and the photons were entangled with each other, the electrons became entangled, a process called entanglement swapping. This was not a simpler experiment than Aspect's. It was a more complex one, designed specifically to close the loopholes that Aspect's experiments had left open. They closed all the major loopholes simultaneously. Previous experiments had closed individual loopholes. Aspect had addressed the locality loophole. Later experiments had improved detection efficiency, but no single experiment had closed every significant loophole at the same time. Critics could always point to at least one remaining escape route. A truly definitive Bell test required eliminating all of them together. The Delft experiment used entangled electrons rather than photons. Electrons in nitrogen vacancy centers in diamonds, separated by 1.3 kilometers at opposite ends of the Delft University campus. The detection efficiency was high enough to close the detection loophole. The separation and the random switching of measurement settings closed the locality loophole. Independent quantum random number generators, not humans, not computers, but quantum processes, chose the measurement settings, addressing the freedom of choice loophole. Every major objection, every remaining escape route, closed simultaneously. The results: Bell's inequality violated, definitively, convincingly, with no remaining argument for a classical explanation. The physics community had known for decades that quantum mechanics was right and local hidden variables were wrong. The Delft experiment was not a surprise. It was a closing of accounts, a formal, airtight demonstration of what everyone already believed, but could not yet prove beyond any loophole-based doubt. Between the Delft experiment in 2015 and the Nobel Prize in 2022, additional loophole-free Bell tests were conducted by teams at NIST in the United States, at the University of Vienna, and at other laboratories around the world. Each confirmed the violation. Each used different experimental approaches, different particle types, different loophole-closing strategies. The results were all the same. The scientific community had not needed the Nobel Prize to accept the conclusion. By 2015, the question was settled in the minds of physicists. The Nobel Prize was a formal recognition, the institution that represents the highest level of scientific achievement, officially endorsing what the experimental record had established beyond reasonable doubt. 4 years later, 3 of the men who had built the experimental case for this result received the world's most prestigious scientific prize. On the 4th of October 2022, the Royal Swedish Academy of Sciences announced the Nobel Prize in Physics. Alain Aspect, John Clauser, Anton Zeilinger. The official citation read, "For experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science." This is a quiet sentence for what it contains. Let us translate it carefully. Experiments with entangled photons. They built the instruments and designed the tests that could actually probe the question Bell had made testable. Establishing the violation of Bell inequalities, they proved experimentally, definitively, with no remaining scientific controversy, that local hidden variables do not exist, that the universe is not made of particles carrying predetermined information, sitting in definite states, affecting each other only through local interaction. Pioneering quantum information science. The implications of what they proved extend beyond philosophy. Entanglement is a resource. It can be used. The quantum computers and quantum communication networks now being built around the world rest on the foundation of what Clauser, Aspect, and Zeilinger demonstrated. But the scientific applications, significant as they are not what this video is about. What this video is about is what those first 8 words mean. The violation of Bell inequalities has been established. Local realism is false. The most prestigious scientific institution on Earth has officially confirmed that the universe does not behave locally, that objects do not have definite properties independent of measurement, that entangled particles separated by any distance, a meter, a kilometer, a light year, a galaxy, are not 2 independent things but one system, one quantum state, extended across space in a way that has no classical analog and no comfortable interpretation. They did not win the Nobel Prize for proving something right. They won it for proving something wrong, something we had believed, without question, since before we had words for it. There is a remarkable asymmetry in this story. The experimental work, the actual running of the tests, the collection of the data, the closing of the loopholes, required 50 years of sustained effort, multiple generations of physicists, and an enormous investment of time and resources. The theoretical work, Bell's original insight, required one man working in his spare time over the course of perhaps a year. This asymmetry is common in the history of science. A theoretical insight is cheap. An experimental confirmation is expensive. The insight points the way. The experiments walk the path. And the path, in the case of Bell's theorem, turned out to be longer and more technically demanding than anyone anticipated when Bell published in 1964. Clauser's 1972 experiment demonstrated the violation with loopholes. Aspect's 1982 experiment closed the locality loophole. The Delft experiment in 2015 closed all major loopholes simultaneously. Between those experiments, dozens of other groups contributed results that confirmed the violation, closed individual loopholes, extended the distances, and improved the precision. The scientific case built up, piece by piece, confirmation by confirmation, until there was nothing left to doubt. The Nobel Committee waited 7 more years after the Delft experiment. This is not unusual. Nobel Prizes are frequently awarded decades after the work they recognize, once the significance of the result has been fully absorbed by the field and its implications have begun to be realized. The prize for the discovery of the Higgs boson was awarded in 2013, 1 year after the discovery, unusually fast. The prize for quantum entanglement came 50 years after Bell's theorem and 7 years after the loophole-free confirmation. The slowness is not a criticism. It reflects the depth of what was being absorbed. The implications of Bell's theorem take time to sit with. They are still being worked out. 50 years passed between Bell's theorem in 1964 and the loophole-free experiments in 2015. 50 years of experimental work, of gradually closing escape routes, of slowly eliminating every possible classical explanation for what the data was showing. During those 50 years, some physicists hoped the experiments would fail. Not because they wanted quantum mechanics to be wrong, quantum mechanics clearly worked, and no one doubted that. But because some physicists, following in the tradition of Einstein, hoped that the universe would turn out to be locally real after all, that some subtler theory with hidden variables would emerge to explain the quantum predictions without requiring non-locality, that the gap between the classical and quantum worlds would prove navigable. Bell himself was among those who privately hoped this. He found quantum mechanics, as he wrote, not professional, too vague about the nature of reality, too reliant on the concept of measurement without a clear theory of what measurement was. He spent his career hoping someone would find a locally realistic theory that reproduced quantum mechanics predictions. His own theorem made it impossible. "I am a quantum engineer," Bell once said, "but on Sundays I have principles." On Sundays, in his spare time, in the margins, he asked what quantum mechanics actually meant. He never found a satisfying answer. He died in 1990, before Aspect's loopholes were fully closed, before the Delft experiment, before the Nobel Prize. He died with the question still officially open. The question is no longer open, and what the answer says about the nature of reality is something that even the physicists who established the answer have not fully agreed on how to interpret. There is a detail worth holding before we get to what the answer means. John Clauser, one of the 3 Nobel laureates, did not expect the result he got. He ran the experiment in 1972, hoping to vindicate Einstein. He thought hidden variables were real. He thought quantum mechanics, for all its computational success, was describing shadows on a cave wall rather than the things themselves. He built the apparatus because he wanted to test Bell's theorem, not because he was certain quantum mechanics would win. When the data came in and the Bell inequality was violated, Clauser was disappointed. He did not immediately accept the result as definitive. He continued to look for loopholes, for errors, for any way the data could be reconciled with a locally realistic universe. He was not persuaded by his own experiment for years. This is not a story about a scientist ignoring inconvenient data. It is a story about how difficult it is to accept that the universe does not work the way your deepest intuitions tell you it should. Clauser's intuitions were Einstein's intuitions, the intuitions of a mind built for a world of separate objects at definite locations, carrying definite properties, affecting each other through local interaction. Those intuitions are not wrong as practical tools. They are wrong as fundamental descriptions of reality. The cup on the table is real enough for practical purposes. Local realism works at the scale of cups and tables and human beings. It is an excellent approximation. It is the right framework for building bridges and navigating cities and predicting whether it will rain. It is not how the universe works at its foundation. Now comes the part that requires care. It is tempting, when discussing quantum non-locality, to overstate what has been proven. Some popular accounts suggest that the violation of Bell's inequality means information can travel faster than light, or that consciousness creates reality, or that quantum mechanics proves some version of mysticism or idealism. These are overstatements, some of them serious distortions, and they obscure what is actually strange and actually proven. Let us be precise, and let us be patient with the precision, because this is a place where popular accounts of quantum mechanics frequently go wrong, and the wrong version is both more exciting and less true than the right version. The violation of Bell's inequality does not mean you can send information faster than light. This is worth understanding clearly, because it is one of the most common misunderstandings of quantum non-locality. When you measure your entangled particle, you get a random result. You do not get to choose the result. You cannot make your particle spin up rather than spin down. The quantum outcome is genuinely random, not pseudo-random, not determined by hidden variables you do not know, but fundamentally, irreducibly random. This is one of the things Bell's theorem establishes. There are no hidden variables that predetermine the result, because you cannot control the result you get. You cannot use your measurement to send a message. You measure, you get a random result. Your distant partner measures, they get a correlated random result. The correlation is there, but to see the correlation, you have to compare your results. And comparing results requires a classical communication channel, which is limited by the speed of light. The non-locality is real. The instantaneous correlation is real. The ability to exploit it for faster-than-light communication is not. What the violation does mean is stranger than faster-than-light communication. And it requires sitting with discomfort to understand. Local realism has two components: locality and realism. Bell's theorem says they cannot both be true. One of them, or both, must be abandoned. The experiments confirm the violation. The interpretation of what must be abandoned remains genuinely contested. The majority of physicists today abandon realism rather than locality. They accept a picture in which quantum systems do not have definite properties before measurement. A particle does not have a definite spin before you measure it. The question, what is the spin of this particle right now, does not have an answer, not because we do not know, but because there is no fact to the matter. Measurement does not reveal a pre-existing property. It creates the property. This is a genuinely strange position to take about the physical world. It means that reality, at the quantum level, is not made of things with properties. It is made of possibilities. Quantum states are not descriptions of what particles are. They are descriptions of what particles might become when interacted with. The universe, at its foundation, is not a collection of objects. It is a collection of potentialities. The physicist Werner Heisenberg, one of the founders of quantum mechanics, wrote that the atoms and elementary particles of quantum mechanics form a world of potentialities rather than one of things or facts. This was not a casual metaphor. He meant it as a literal description of the ontology, the fundamental stuff of the universe. At the scale of everyday life, potentialities resolve into actualities so fast and so completely that we never notice the underlying uncertainty. The process by which this happens has a name: decoherence. Decoherence is what happens when a quantum system interacts with its environment. Every interaction is, technically, an entanglement. The measuring device and the particle become entangled. The measuring device and the air molecules around it become entangled. The air molecules and the floor become entangled. The floor and the building become entangled. The entanglements proliferate outward at an extraordinary rate, spreading the quantum information of the original system across an environment of astronomical complexity. The effect of this spreading is to destroy the quantum coherence of the original system. The superposition, the existence in multiple states simultaneously, does not literally collapse in the way the textbook picture suggests. Rather, the quantum information about which state the system is in becomes encoded in the correlations between the system and a vast, complex, essentially unknowable environment. For practical purposes, the superposition has resolved. The particle appears to be in a definite state. The cat appears to be either alive or dead. The cup appears to be definitely on the table. But appears is doing significant work in those sentences. The quantum superposition has not been eliminated. It has been distributed. The cat is still, in the full quantum description, in a superposition of alive and dead, but it is entangled with the air molecules of the room, which are entangled with the floor, which are entangled with the building, which are entangled with the earth, in a web of correlations so vast that no measurement we could ever perform would reveal the original superposition. For every practical purpose, the superposition is gone. It is irretrievably gone, but it is not literally, fundamentally, ontologically gone. This is what classicality means in the quantum picture. Not that the quantum laws stop applying, not that there is a genuine boundary between quantum and classical, but that the quantum coherence of macroscopic systems is so completely distributed into environmental degrees of freedom that it can never be recovered. And so the system behaves, for all practical purposes, like a classical system with definite properties. The cup is real. The table is real. You are real. But the reality that you and the cup and the table are built from is not made of the same stuff you are made of. The atoms in the cup on the table interact with so many other atoms so constantly that their quantum states decohere, lose their quantum coherence within incomprehensibly small fractions of a second. The cup is, for all practical purposes, in a definite state. It has definite properties. The quantum uncertainty has been washed out by the constant bath of interactions that constitute macroscopic physical existence. But the washing out is not elimination. It is suppression. The quantum nature of the cup is still there at the level of its constituent atoms. The non-locality is still there, in the entanglements that form and dissolve constantly as particles interact. The potentiality is still the substrate from which the apparent definiteness of the macroscopic world emerges. This means the universe, at the quantum level, is not made of things in definite states. It is made of possibilities, of probability amplitudes, of quantum states that exist in superposition until observation forces a specific outcome. The classical world of definite objects in definite locations is not fundamental reality. It is a large-scale emergence from a quantum substrate that is radically less definite. But abandoning locality is also an option, and some physicists take it. David Bohm developed a version of quantum mechanics, now called Bohmian mechanics, or pilot wave theory, in which particles do have definite positions and trajectories at all times, but they are guided by a wave function that is genuinely non-local. Changes to the wave function here propagate instantaneously everywhere. The non-locality is explicit and real. The particle always has a definite position. Realism is preserved. Locality is not. Either way, something you thought was fundamental turns out not to be. The interpretations of quantum mechanics are, at this point, a collection of uncomfortable choices. Each one survives Bell's theorem. Each one requires giving up something that feels essential. The Copenhagen interpretation, the original, the pragmatic, the one most physicists default to in practice, says simply, stop asking what is happening between measurements. The wave function is not a description of reality. It is a calculational tool that gives you probabilities for measurement outcomes. What happens in between measurements is not a question physics can answer. Perhaps it is not a question that has an answer. This is uncomfortable because it makes measurement, and therefore observers, fundamental to physics. A universe with no observers in it, a universe before any life existed to make measurements, is, in strict Copenhagen terms, a universe in which quantum states never collapsed. The quantum mechanical description of the early universe would be a vast superposition, never resolving into definite outcomes. That resolution required observation, and observation required observers, and observers required a universe with definite enough properties to produce them in the first place. The Copenhagen interpretation sidesteps this by refusing to ask the question, shut up and calculate. The many worlds interpretation, developed by Hugh Everett in the 1950s, takes a different approach. It says, the wave function never collapses. Every possible outcome of every quantum measurement actually occurs in different branches of the universal wave function. When you measure a particle and find it spinning up, there is another version of you in another branch who found it spinning down. Both outcomes occur. Both are real. There is no collapse. There are only more and more branches, proliferating with every quantum interaction. Everett developed this interpretation as his PhD thesis at Princeton under the supervision of John Wheeler. The reaction from the physics community was largely dismissive. Bohr, whose Copenhagen interpretation was the dominant framework, found it unnecessary. Why introduce countless parallel worlds when the pragmatic Copenhagen approach worked just as well? Everett left academia after his PhD and worked for the rest of his career in defense consulting. He is said to have been bitter about the reception his idea received. He died in 1982, before the many worlds interpretation experienced its significant revival. The revival came partly through the work of David Deutsch, who argued in the 1980s that many worlds was not just a philosophical curiosity, but the natural framework for understanding quantum computation. A quantum computer, in the many worlds picture, performs its computations by exploiting the parallel branches, effectively computing in multiple universes simultaneously and combining the results. The computational power of quantum computers is, in this interpretation, the power of parallel processing across multiple worlds. Whether or not this picture is literally true, it has proven heuristically powerful. Many of the physicists and computer scientists who build quantum computers find many worlds the most natural framework for thinking about what the quantum computer is doing. The many worlds interpretation preserves realism. Quantum states are real. Measurement outcomes are real, at the cost of an enormous and unverifiable ontological expansion. Every quantum event branches reality. Every measurement creates new worlds. The universe contains not one history, but an incomprehensibly vast collection of histories, most of which we will never have access to. Relational quantum mechanics, developed by Carlo Rovelli, takes perhaps the most radical approach. It says that quantum states are not absolute. They are relational. A particle does not have properties in itself. It has properties relative to a particular observer or measuring device. There is no view from nowhere. Reality is not a single observer-independent structure. It is a web of relationships between systems, each of which has a perspective on the others, and no perspective is more fundamental than any other. These three interpretations are not the only ones. Cubism, quantum Bayesianism, treats quantum mechanics as a theory about an agent's beliefs and actions rather than about external reality. In Cubism, the wave function is not a description of the world. It is a description of an agent's expectations. When the wave function collapses, nothing collapses in the world. An agent updates their beliefs. The non-locality disappears because there is no wave function of the world to be non-local. There are only agents, making measurements, updating beliefs. Cubism is philosophically interesting and scientifically controversial. It solves the measurement problem by dissolving it, by insisting that measurement is the fundamental concept and that asking what is happening in the world between measurements is a category error. Critics find it solipsistic, or at least idealist, in ways that seem to privilege the existence of minds over the existence of the physical world. There is consistent histories, which defines reality in terms of sets of histories that can be assigned consistent probabilities. Consistent histories is an attempt to make quantum mechanics compatible with the idea that the universe has a definite history, that it is possible to talk about what happened before a measurement was made, as long as you restrict yourself to histories that are mutually consistent. It is technically sophisticated and philosophically austere. There are modifications of quantum mechanics that add explicit collapse dynamics. The GRW theory, named for Girardi, Rimini, and Weber, adds a small random collapse to the Schrödinger equation. Particles have a tiny probability per unit time of spontaneously collapsing their wave function. For a single particle, this happens so rarely that it is undetectable. For a macroscopic object with 10 to the power of 23 particles, collapses are happening constantly, and the object is effectively always in a definite state. The collapse is physical, spontaneous, and requires no observer. These three interpretations are not the only ones, but they represent the main philosophical directions. There are modifications of quantum mechanics that add explicit collapse dynamics, the GRW theory, for example, which try to give a physical account of when and how the wave function collapses. Every one of them survives Bell's theorem. Every one of them requires abandoning something. The only disagreement is what to sacrifice. Every interpretation of quantum mechanics that survives Bell's theorem requires you to give up something you thought was real. The only disagreement is what you sacrifice. Here is the final thing to say, and it requires the most care. There is a temptation, when confronted with the implications of quantum non-locality, to reach for metaphysical comfort to say that quantum mechanics proves consciousness is fundamental, or that Eastern philosophy had it right all along. These moves are understandable but wrong. Quantum mechanics does not say these things. It says something far stranger and more austere, that the classical picture of reality is not the fundamental picture. Niels Bohr reportedly said that if quantum mechanics has not profoundly shocked you, you have not understood it yet. He did not mean this as an invitation to mysticism. He meant it as an honest description of the epistemic situation. The quantum world is genuinely alien to intuition. Richard Feynman said simply, "Nobody understands quantum mechanics. Not that the mathematics is incomprehensible, but the question of what the mathematics describes remains genuinely open. Not because we have not been clever enough, Because the world at the quantum level may be the kind of thing that cannot be described without distortion in the language of everyday experience. This is worth sitting with. We are not in a situation where we lack data. We have extraordinary amounts of data. We are not in a situation where the theory fails to predict. The theory predicts with spectacular precision. We are in a situation where the theory works perfectly and we cannot agree on what it means about the nature of reality. This is unusual in the history of science. Usually, a working theory comes with a picture, a model of what the world is like, that explains why the theory works. Newton's mechanics came with a picture of particles and forces. Maxwell's electromagnetism came with a picture of fields filling space. General relativity came with a picture of curved space-time. The model and the mathematics go together. You know what you are calculating, not just how to calculate it. Quantum mechanics has the mathematics without the agreed-upon picture. The Schrödinger equation tells you how the wave function evolves. The Born rule tells you how to extract probabilities from the wave function. The predictions are clear and precise, and verified to extraordinary accuracy. But whether the wave function represents something physically real, or is merely a calculational tool, or represents our knowledge rather than the world, is a question on which brilliant physicists have disagreed for a century and continue to disagree today. One useful way to think about this situation: imagine you are given a very accurate map of a city you have never visited. The map tells you how to navigate from any point to any other point. Every street name is correct. Every distance is accurate. The map works perfectly in every practical sense. But you have never seen the city. You do not know what the streets look like, what the light is like in the morning, what sounds fill the air. The map gives you operational knowledge without giving you knowledge of what the place actually is. Quantum mechanics is that map. Bell's theorem proved the map is not describing the classical city we assumed we lived in. The experiments confirmed this beyond any remaining doubt. But what city the map is actually describing, what reality is actually like at the quantum level, is a question the map itself cannot fully answer. What the map says with absolute confidence is this: not locally real. The universe is not locally real. This is an unusual situation in science. Usually, when a theory works, it comes with a picture, a model of what the world is like that explains why the theory works. Atoms explain thermodynamics. Curved space-time explains gravity. The germ theory of disease explains infection. The model and the mathematical framework go together. You know what you are calculating, not just how to calculate it. Quantum mechanics is different. The mathematical framework is not in dispute. The Schrödinger equation, the Born rule, the commutation relations, these are as settled as anything in science. But the model, the picture of what the world is like that these equations are describing, is genuinely contested. Physicists disagree, not about the equations, but about what the equations mean, about whether the wave function is real or just a calculational tool, about whether particles have definite properties between measurements, about whether the universe has one history or many. This disagreement has persisted for a century. It is not a sign of failure. It is a sign of the genuine difficulty of the question. One useful analogy: imagine you are shown a very detailed and accurate map of a city you have never visited. The map tells you how to get from any one point to any other point. It tells you the distances, the street names, the landmarks. If you use the map, you will always arrive where you intend to go. The map works perfectly, but you have never seen the city. You do not know if the streets are wide or narrow, what the buildings look like, what the light is like in the morning. The map gives you operational knowledge, knowledge of how to navigate, without giving you experiential knowledge of what the place is actually like. Quantum mechanics is the map. Bell's theorem and the experiments it generated proved that the map is not describing the classical city we thought we lived in. But the experiments cannot show us what the real city looks like. They can only show us what it is not. What it is not. Locally real. What it is. A question that remains open. What we have is the data. And the data says the universe is not locally real. You are made of atoms. Those atoms are made of protons and neutrons and electrons, which are in turn made of quarks and governed by quantum fields. Every atom in your body, every particle in every atom, is subject to quantum mechanics. The strangeness we have been discussing is not a property of exotic laboratory experiments. It is a property of the substrate from which you are built. The atoms in your body were forged in stars. Those stars condensed from gas clouds. That gas descended from the Big Bang. And in the first instance, after the Big Bang, everything in the observable universe was compressed into a region incomparably smaller than anything we can see today. Every particle, every field, every quantum of energy was in causal contact with everything else. The entanglements formed in those first moments have been distributed and redistributed by billions of years of subsequent interaction, hidden in correlations between particles, separated by the full width of the observable universe, correlations so complex and spread out that no conceivable measurement could recover them. The universe may be, at its deepest level, one vast, entangled system. Not as a mystical claim, as a mathematical one. The quantum state of the universe cannot be fully described as a collection of independent local states. There is one wave function. Everything is part of one system. The decoherence hides this from our measurements. The macroscopic world behaves as if things are separate, but the separation is behavior, not foundation. The atoms in your body were forged in stars. Those stars condensed from gas clouds. That gas descended from the Big Bang. In the first moments after the Big Bang, everything in the observable universe was compressed into a region incomparably smaller than anything we can see today. Everything that would ever exist, every particle, every field, every quantum of energy was in causal contact, in interaction with everything else. The entanglements formed in those first moments have been disrupted by billions of years of subsequent interaction. Decoherence, the process by which quantum systems lose their coherence through interaction with their environment, has, at the scales of everyday life, effectively washed out the quantum weirdness. The cup on the table does not exhibit quantum superposition. Your body does not tunnel through walls. But at the fundamental level, the substrate from which all of this emerges is quantum mechanical, non-local, entangled, not made of separate, definite, locally determined things. The separation you perceive between yourself and the wall, between this planet and the star nearest to it, between this galaxy and the next, these separations are real at the scale you inhabit. They are effective. They are the appropriate description for a being built at your scale, living in your world, navigating the macroscopic reality of everyday existence. They are not fundamental. If locality is not fundamental, if things that appear separate are not truly separate, what does that mean for you? It means the universe you have lived in every second of your life, the universe with edges and distances and separate objects with definite properties, is not the deepest description of what is. The Nobel Prize was not awarded for a discovery about particles. It was awarded for the proof that the universe you live inside, the one with edges and distances and separate things, is a story you tell yourself. A useful one, a necessary one, but not the real one. There is one more implication of entanglement that physicists are only beginning to take seriously, and it is perhaps the most radical of all. The violation of Bell's inequality does not just say that particles can be correlated across distances without a classical explanation. It raises a deeper question about what space is. In classical physics, space is the stage on which events occur. It is a container, a three-dimensional structure in which objects are embedded. Objects have positions in space. They move through space. They influence each other through forces that travel through space. The container is real, but it is not made of anything. It is just there, as the background in which everything else happens. In general relativity, Einstein showed that space is not a fixed background. It can curve in response to mass and energy. What we experience as gravity is the curvature of space-time. Objects do not follow curved paths because a force is pushing them. They follow straight paths through curved space-time. Space is dynamic, not fixed. But even in general relativity, space is still the fundamental container. It still has a structure that is independent of the things within it. The curvature is real, but the space being curved is still real in the traditional sense. Quantum entanglement challenges this. If two particles are genuinely non-locally correlated, if they are, in some meaningful sense, one thing distributed across space rather than two things connected by a relationship that travels through space, then what does that say about the space between them? Some physicists, most notably Juan Maldacena and Leonard Susskind, have proposed that entanglement and the geometry of space are not separate phenomena. They have proposed, based on work in the framework of string theory and holography, that space-time geometry itself might emerge from entanglement, that what we experience as space, the distances between things, the connectivity of regions, the very structure of the three-dimensional world, might be a macroscopic emergent property of the quantum entanglement between microscopic degrees of freedom. This is speculative. It is far from established physics, but it is being taken seriously by serious physicists, and it follows logically from the direction that quantum mechanics has been pushing our understanding of space since Bell. If entanglement creates space, if the geometry of distance is a large-scale pattern in a quantum web of correlations, then the violation of Bell's inequality is not just saying that particles can influence each other faster than light. It is saying that the very concept of faster than light, the very concept of distance as a real, fundamental thing, is built on a foundation that quantum mechanics reveals to be emergent rather than bedrock. This is speculative, but the speculation is motivated by real physics, and it is where the thread that Bell pulled in 1964 may eventually lead. The real one is harder to tell. It may be impossible to tell in the full sense, not because the truth is beyond human understanding in principle, but because human language and human intuition were built for the approximation, not for the truth. The words we have, particle, position, spin, measurement, locality, were all developed in the context of the classical world. Applying them to the quantum world is like trying to describe a symphony using only the vocabulary of color. The translation is always partial. Something is always lost. We have mathematics for the truth, quantum mechanics, precise and predictive and verified to extraordinary accuracy. But the translation of that mathematics into words, into images, into a picture of what is actually happening remains incomplete and contested and deeply uncomfortable. This is not a counsel of despair. It is an honest assessment of where we are. The experiments have told us something real and important about the universe. The universe is not locally real. That is a statement with enormous implications, even if we cannot yet fully articulate what those implications are. Physics has been in this position before. When general relativity was first formulated, the idea of curved space-time was almost impossible to visualize. The notion that massive objects warp the geometry of space itself, that what we experience as gravity is the curvature of a four-dimensional space-time manifold, this was described by contemporaries as incomprehensible. It is still, in some deep sense, incomprehensible in the way that direct perception is comprehensible. But it is workable. It makes predictions. It guides understanding. It eventually became familiar enough to be taught in undergraduate physics courses. Something similar may happen with quantum non-locality. The strangeness may not go away. It is too deep for that. But it may become familiar. The vocabulary may develop. The pictures may form, or it may not. The quantum world may be permanently resistant to the kind of intuitive understanding that makes gravity, strange as it is, eventually graspable. The non-locality, the superposition, the entanglement, these may be features of a reality that is simply irreducibly different from anything that a mind built for the macroscopic world can directly grasp. Either way, the experiments have spoken, and the experiments do not lie. John Bell spent his Sundays on this problem. He published further work on quantum foundations throughout his career, papers on the meaning of the wave function, on the nature of measurement, on what quantum mechanics required of any account of reality. He was never satisfied with the Copenhagen "shut up and calculate" response. He wanted to know what was actually going on. In his last years, Bell was cautiously optimistic that a solution might be found, not within quantum mechanics as currently formulated, but through some deeper theory that quantum mechanics was an approximation to, the way Newton's mechanics is an approximation to general relativity. He hoped that the right deeper theory would restore something like local realism, or at least make the non-locality less mysterious. He did not live to see the loophole-free experiments that definitively closed the question. He died of a brain hemorrhage in 1990 at the age of 62. The death came unexpectedly, shortly after he had been nominated for the Nobel Prize, a nomination that, had he lived, would almost certainly have led to the award that eventually went to Alain Aspect and Zeilinger. His legacy is the problem he made testable. Before Bell, the question of whether local realism was true was a philosophical question, important, interesting, but outside the reach of experiment. Bell's insight was that philosophy and physics were not as separate as people thought, that a carefully posed philosophical question about the nature of reality could have an experimental answer. The answer, when it came, was not the one Bell hoped for. The universe is not locally real. The world Bell wanted to live in, a world of definite particles at definite locations, connected by local interactions following deterministic laws, does not exist at the fundamental level. He would have found this deeply unsatisfying. He made the question answerable anyway. And that is a more significant contribution than finding the answer you hoped for. John Bell spent his Sundays on this problem. He never found a satisfying answer. He made the problem testable. He made it empirical. He gave the universe a question it could answer. The universe answered. The answer is not local, not real in the classical sense, not separate, not definite until observed, and perhaps not even then, depending on which interpretation you choose to live with. This is what three men were given the Nobel Prize for in 2022. Not for a discovery that made the universe more comfortable, for a discovery that made it less. And here is the final thing that needs to be said, because it is easy to hear all of this and feel that it has nothing to do with you, that the quantum world is a remote, technical, specialist domain, interesting to physicists, irrelevant to everyone else. That the cup on the table is still real, the star still exists, the particle in your hand still spins, and none of the quantum strangeness touches the world you actually live in. This is true at a practical level. The quantum strangeness is washed out by decoherence at every scale you navigate. Your daily life will not be disrupted by the violation of Bell's inequality. You will never directly perceive the non-locality that the experiments have proven. But the non-locality is there. The entanglement is there. The quantum substrate from which the classical world emerges is there, under everything, at every moment. The atoms in your body are quantum objects. The particles that make them up are quantum objects. The fields that govern their interactions are quantum fields. The entire macroscopic world is a pattern that emerges from a quantum foundation, a foundation that Bell and Clauser and Aspect and Zeilinger have shown us is nothing like the foundation. There is a question that comes up whenever quantum non-locality is discussed in public, and it deserves a direct answer. Does this mean everything is connected? Is the universe, in some literal sense, one thing? The careful answer is yes and no, and the distinction matters. In the mathematical sense, the universe has a single wave function. The quantum state of the universe is one object, not a collection of independent objects. Everything that has ever interacted with anything else is, in the technical quantum mechanical sense, part of one entangled system. The separateness that appears at the macroscopic level is real, as a practical description, but not as a fundamental one. But this does not mean that a thought you think in Poznan influences a star in Andromeda. It does not mean that human consciousness has a special role in shaping reality. It does not mean that quantum mechanics validates any particular spiritual or philosophical system about the unity of all things. The non-locality is real. The entanglement is real. But the entanglement between you and a distant star is not an entanglement that you can exploit, feel, or use. The decoherence has made it inaccessible. The correlations are there, buried in the quantum state of a universe so large and complex that recovering them is not merely practically impossible, but effectively meaningless. What the non-locality means, practically, is narrow and specific. Pairs of particles, carefully prepared in a laboratory, can be entangled in ways that violate Bell's inequality and demonstrate genuine quantum correlations. Those correlations can be used for quantum cryptography, quantum computing, quantum communication. They demonstrate that the classical picture of reality is not the fundamental picture. They do not give us access to cosmic consciousness or allow us to send messages to ourselves in the past or permit us to influence events at arbitrary distances. The universe is stranger than the classical picture allows. It is not as strange as the popular imagination sometimes suggests. What it is, exactly, remains the open question. There is one last thing to say before we let the silence carry the rest. The history of science is a history of displaced certainties. We were certain the Earth was at the center of the solar system. We were certain the continents did not move. We were certain atoms were indivisible. We were certain the universe was static and eternal. Each certainty fell when the evidence became impossible to ignore. Local realism is the latest certainty to fall, the deepest one yet. Not a certainty about what the universe contains or how it is arranged, but about what it is, about the fundamental nature of the stuff from which everything is made. The experiments have been done. The Nobel Prize has been awarded. The certainty is gone. What replaces it is not chaos. The practical certainties remain. The cup is still on the table, the star still burns, the bridge still stands, the predictions still work. The approximation is still useful, still reliable, still the right framework for navigating the world at human scale. But the foundation has changed. Beneath the approximation, beneath the reliable predictions and the solid objects and the local causes and the definite properties, there is something else. Something that does not have a comfortable name. Something that the experiments have pointed toward without fully revealing. Something that the next century of physics will spend its time trying to understand. Something spookier than Einstein was willing to accept. Imagine two particles. They were entangled once, their quantum states linked by an interaction long past. They have traveled apart. Perhaps they are across a laboratory. Perhaps they are across a galaxy. The distance at the quantum level is not meaningful. You measure one. Instantaneously, not after a light-speed delay, not after any delay, the other responds. Not because a signal traveled between them, because they were never, in the way that matters, truly separate. Einstein called this spooky action at a distance. He meant it as a criticism, as evidence that quantum mechanics must be wrong, that any theory that predicted such a thing had to be missing something, a hidden variable, a deeper description, a more complete account that would restore the sanity of a locally real universe. He was one of the greatest physicists who ever lived. He spent decades believing he was right. He died believing he was right. He was wrong. The action is real. The distance is the illusion. And the universe, the one you have lived in every second of your life, the one that feels solid and separate and definite and local, is spookier than Einstein was willing to accept. It is spookier than any of us were built to feel. But it is what the experiments say. And the experiments do not lie.